So, dang it. Lesson 1.4, rational expressions. Here's what we're talking about in the lesson. Domain. Over here. Can divide by 0, yes? So here x would not be allowed to equal -5. Otherwise the fraction would be undefined. So let's take a look at the problem at hand. X divided by x squared minus x minus 12. One little tiny thing we need to do first before determining the domain. Factor the denominator. You need to look at it in factored form. Pretty easy to factor. Scratch that. Very easy to factor. How does it factor? X minus 4, x plus 3. So you no sweat. Now that we can view the denominator in factored form, it's very clear, hopefully very clear, which two x values don't work. Positive 4, negative 3. X cannot be positive 4, x cannot be negative 3. Now if you want to use that set builder notation, you can say, all right, x, all values of x such that x does not equal 4 or negative 3. I'm okay if you state it that way. If it's just a couple of excluded values, set builder notation is really the easiest way. If you're insistent on using interval notation, which is fine, not that there's anything wrong with that. In interval notation, the domain would be negative infinity to negative 3, parenthesis, union. Now where? Negative 3 all the way up to 4, union 4 to infinity. So you can do it that way if you want. Okay, I think we're ready to move on. Any other questions on finding the domain? It's you have to exclude the values that would make the denominator turn into 0, essentially. Okay, pretty easy. Let's move on to whatever the next topic was supposed to be. Oh, simplifying. Equally as easy. Simplify a rational expression. If you're pretty good at factoring, this ought not to be a problem, because it involves a little bit of factoring. Example 2.
Simplify rational expressions.
Nope, that's not what I said. Simplify the expression x squared minus 1 divided by x squared plus x minus 2. Now, I hope that at this point in your mathematical careers, I guess you could call it, or your mathematical whatever, I hope at this point it's clear that the following cannot happen. It cannot happen. And I see this in lower levels of mathematics, and it drives me bonkers. Students will say, hey, look at this. There's an x squared and an x squared. Boom, see you later. Cannot happen. Not even close to being correct. There's nothing like that anywhere in mathematics that makes that true. Okay? Why doesn't that work, by the way? You can only cancel out common factors. You can only cancel out common factors. Okay? A factor of an expression are the elements multiplying together that equal the product, if that makes sense. Here's what I mean by that. If we wanted to simplify, I don't know, 8 divided by 12. I know you could all do this in your head pretty quickly, probably. But what actually is happening here when you're simplifying this in a matter of seconds? This is actually what you're doing. You're saying, all right, 8 is 2 times 2 times 2, and 12 is 2 times 2 times 3. Now what do? You cancel out the common factors. What are factors? Factors are the individual terms multiplying together that equal the entire product. So you cancel out the 2's, and you're left with 2/3. Okay, you can cancel out common factors, right? But you can't do this. All right, 8 is the same as 10 minus 2, and 12 is the same as 6 plus, or let's do 14 minus 2. Because that's still true, right? This is still a true expression. But now we're going to cancel out the 2's, right? Do you end up with an equivalent expression that way? No, you can't do that. You can't cancel out parts of a term. You can only cancel out factors. Is that clear? You can't just cross out the x squared. What do we have to do here? Okay, then. X minus 1. X plus 1. And then the denominator, x minus 1, x plus 2. Well, I'll agree with that. And we have an x minus 1 factor, and over here we have an x minus 1 factor. You can cancel out the common factors, but you can't just cancel out pieces of an expression. Common factors, yes. Yeah?
Does that mean we can cancel it out when they're like multiplying?
Yep, exactly. So now we have x plus 1 divided by x plus 2. And again, same type of problem I see very often. Can you just cross off the x's? No. Those are parts of the term. They're not factors. So anyway, that is what is meant by simplifying rational expressions. Okay? Also pretty easy. Essentially, it's really just practicing factoring in a way. So let's move on. Where are we? Simplified domain. Multiply and divide. True or false? You have to have common denominator to multiply fractions. False. You don't have to have common denominator. How do you multiply fractions together? Straight across. Numerator to numerator, denominator to denominator. It does not matter if they're the same or not, which is really, really nice. So here's an example. Multiply the expression x squared plus 2x minus 3 divided by x squared plus 8x plus 16 multiplied by 3x plus 12 divided by x minus 1. Now, there are potentially two ways probably to do this, but there's only one way that's the best way. Factor first and cancel out common factors, and then multiply straight across. That'll make things so much easier. Factor, cancel out common factors, and then multiply straight across. So anything that you think can factor, factor it. And then there are some tips and tricks, I guess, when specifically multiplying. So x squared plus 2x minus 3, that's going to be x plus 3 times x minus 1. X squared plus 8x plus 16. Hey, that's a perfect square trinomial. X plus 4 times x plus 4. A perfect square trinomial means it's a trinomial that factors into two identical binomials. X plus 4 times x plus 4. Now this type of factoring, or simplifying, is called cross-canceling. You need to listen very carefully. You're listening very carefully. Cross-canceling only works on multiplication problems. What I mean by cross-canceling is you see an x plus 4 here, and then on the other fraction you see an x plus 4. You can cross-cancel those only while multiplying, never with addition or subtraction. Okay? X plus 4, they can cancel. X minus 1, and then the x minus 1 down here can cancel. Now you're ready to multiply straight across. 3 times x plus 3 in the numerator. Divided by x plus 4. Oh, we're all still waiting for these problems to get difficult, right? Why does math have to be so easy all the time? Darn it. No, it's just easy. Inherently, it's easy. Right? Not always. Not always. We'll get to some pretty funky stuff here in this class. What's that? No. See, that's not lazy. That's smart. That's conserving resources. Yeah. I would leave it. Leave it in factored form. Yep. Division is almost exactly the same as multiplication. Just one little difference right at the beginning of the problem. Let's finish a multiplying problem. Oh, no, sorry. Let's finish a dividing problem. Then I'll have you stand up for just a minute. Get some blood moving, and then we got to really buckle down for these addition and subtraction problems. They're not quite as easy, but it's double the fun. So, x minus 4 divided by x squared minus 4. Sorry, yeah, let's do that. And then a division sign. X squared minus 3x minus 4. X squared plus 5x. 6. Okay, here's what I would do right at the first. And, well, maybe you could try to do two things at once if you're good at keeping track of things. You can't divide fractions. You switch this to a multiply sign and invert the second fraction to its reciprocal. Okay? Now, at the same time, if you want to start factoring, that would be fine. You don't do anything to the first fraction. You leave it alone. So it's x minus 4 over x minus 2, x plus 2. You can change that to a multiply sign. Flip this second fraction to its reciprocal. And at the same time, let's factor. So this bottom expression, if it moves to the top and factors, becomes x plus 2 times x plus 3. And then this expression that was in the numerator is going to hop down to the denominator and also factor, if it can, into x minus 4 times x plus 1. And before multiplying straight across, let's just cross-cancel some common factors. And you don't have to cross-cancel. If they're on the same side, you can also cross them off. But what do we have here? We have an x plus 2, x minus 4, and then there we have an x minus 4. Anything else? So it looks like all we have in the numerator is x plus 3. And in the denominator is x minus 2 times x plus 1. And again, just leave it in factor form. You wouldn't need to multiply those two binomials. Not that it's super important, but some of you might be interested in this. Do you know why we have to flip the second fraction to its reciprocal? Do you know why we do that? I think I see what you mean. Let's take a look at this problem. Let's use numerical values instead of algebraic values. If I asked you to do 2/3 divided by, I don't know, 4/5, Could that not be written like this? You tell me yes or no. Maybe I'm just up in the night. Could that be written like that? It could be, right? Now, tell me what you think about this. Is it okay to multiply a fraction by the same thing on the top and bottom? Is that okay? The same thing on the top as the bottom? Because really what we, like if I multiplied this by 2 over 2, is that okay to do? How come? True. True. And it's just 1. 2 divided by 2 is 1. I'm multiplying that by 1, right? So I can multiply this by anything as long as it's the same on top and bottom. But multiplying that by 2 really isn't going to do much. What if I multiplied it by 5/4 over 5/4? Why in the world would I want to do that? Denominator's gone. And now look at what we have. That's why you multiply by the reciprocal of the second fraction. Okay? Because it cancels this denominator and ends up with the same problem. Anyway. Let's take a little break here. Stand up for a second. Okay. Adding, subtracting. It is recording, yep. Thank you for reminding me. This is where you do have to have common denominators. So, example 450. That's what it seems like, right? Example 5, 3 over x plus x over x minus 2. Now again, just so we can avoid very early on some of the, I don't know if they're very common, but just some of the mistakes I see. In order to get common denominators, I see this. All right, this minus 2 here and minus 2 right there. Okay. I mean, it seems like an okay thing, right? Doesn't that give us an x minus 2 down there? You can't do that. Why can't you do that? Well, think about how you would do this numerically and not algebraic. If I had 1/2 and I wanted to add, I don't know, 3/5. You guys know how to do this with numbers, so just do the same thing with expressions. How would we do this with numbers? Would I just add 3 right there to make that 5? No, you can't do that. What would you do? You times it by something over itself. In this case, 5 over 5, and this would have to be 2 over 2. That's okay to do, because all this is a clever form of 1, and you're multiplying something by 1 doesn't change the value. So do the same thing over here. If I have an x here, I need to have an x over here. If I have an x minus 2 on the right side, I have to have the whole entire x minus 2 on the left side. You can multiply a fraction by 1, and all of these, x over x is just 1, x minus 2 over x minus 2 is just 1. Assuming, I guess, that here x doesn't equal 0 and here x doesn't equal 2. Now, what you're going to need to do is leave the denominator factored, but in the numerator you are going to want to distribute. So in the numerator, simplify that and multiply those together. So you're going to end up with 3x minus 6 over your common denominator plus x squared over the common denominator. And I know you know this, but just to reinforce what you already know, when you're adding fractions that have the same denominator, the answer has also that same exact denominator. It's kind of like you're adding like terms. 1/4 plus 2/4 is how many fourths? 3/4, right? You stay in terms of that denominator you're in. So you don't add the denominators, those stay the same. It's the numerators that add. X squared plus 3x minus 6. Easy peasy lemon squeezy, right? No big deal. Why were you so scared of these? I don't know if you were or not. Maybe you weren't. Let's do part B. Same example, part B. I'm going to try to trick you. I'm going to come up with something that's going to try to trick you here. 1 over x squared minus 1. Subtract 2 over x plus 1 squared. Look at the denominators in terms of their individual factors and then decide what is missing on each side. So the left side. Nobody? Strong side. Come on. Remember the Titans?
Yeah.
Oh, wow. You guys watch TV sometimes, right? No, you study all day long, don't you? Even on the weekends. No time for movies. So, the left side is x minus 1 times x plus 1. And nothing really to do on the right side. Except expand it out, maybe. Ooh, mama. Whoa, okay.
Man, we really skipped ahead to a tough one, didn't we? This side has 2x plus 1 factors. Over here on the left side, we only have one of these x plus 1 factors. So what's missing over here on the left side? Another x plus 1 factor. If the right side has 2x plus 1 factors in the denominator, the left side has to have 2x plus 1 factors. But now the left side has x plus 1, x minus 1. So this one needs an x minus 1. I guess this one isn't so bad. Left side becomes x plus 1 over, oh man, just, what was the phrase, mathematicians are lazy? I'm just going to write LCD right here. That's the LCD. Minus. What happens there in the numerator?
2x minus 2.
2x minus 2, good, over our new found LCD. Ooh. Be very, very careful here. Please be careful in the numerator. What do we get?
Negative x plus 3.
Negative x plus 3. It is negative x plus 3. Why is it negative? That is the correct answer. Negative x plus 3.
Negative 1
This minus sign, doesn't that mean you're just subtracting the entire thing? You're not just subtracting a 2x, you're subtracting a negative 2. Subtracting a negative 2 is a positive 2. Positive 2 combined with a positive 1 is indeed 3. That's just one of these things that it's very, very, very easy to overlook. I know that. I overlook it all the time. It's easy to overlook. It's something you got to try to really watch out for. When you're subtracting an expression, subtract every piece of that expression. Anyway, it's negative x plus 3. And you can't just write LCD as an answer over here. It can't be that way. X plus 1 times x plus 1 times x minus 4. Or you can do x plus 1 squared. You figure right that out.
thought you could have so much fun with rational expressions. You guys didn't even think this was possible. Okay. We're done with 4 topics. How many to go? We've done 4 objectives. 2 more. Okay. Compound fractions. Let's do this. Let's finish this one objective. Then I'll play he, she. How's that? How it should have ended. What did you think I meant? Yes, you did. Oh man. Anywho, a compound fraction. I actually already showed you one. I just didn't tell you it was a compound fraction. This, where was it? Did I pass it up? Oh, I erased it. Dang it. Well, you might remember this from a few minutes ago. If I said, all right, 2/3 divided by, what was it, 4/5, and I wrote it like this. This is a compound fraction right here. It's a fraction numerator, fraction denominator, in the form of a fraction itself. What could be more wonderful? Compound fraction is this kind of thing. But rather than numerical values, we're going to have algebraic expressions as compound fractions. Okay? So, what example are we on? Example 6. Yes, example 6. X divided by y plus 1 over 1 minus y over x. So the idea here is to end up with just a normal rational expression and not a compound fraction. So what that is going to entail is combining this expression right here, x divided by y plus 1, that needs to be combined into a single expression. And then the same thing in the denominator, that needs to be combined into a single expression. And then you change this to multiply. This sign right here, change it to multiply. Flip the bottom fraction upside down. Multiply straight across. That's what we're doing. You following? Okay, so let's start. In the numerator, we need to combine this into one expression. We can't have it as the sum of 2 terms. Bueller. How do we add these 2 together? It's not really as hard as you think. 1 is nice. 1 could be anything. 1 could be y divided by y, for example. Isn't that the same as 1? Yep. Why would y divided by y be so nice? Because this has a y in the denominator. So I'm going to switch this 1 into y over y. Now we can change this into x plus y over y. That was pretty harmless. We didn't lose anybody on that one. No casualties. Same type of thing could be applied in the denominator. We have a 1 right here, so just change that into x over x. And combine that into one fraction. That's going to be x minus y over x. And now we have a single fraction divided by a single fraction. We change this into a multiply problem. So take that bottom fraction, turn it into its reciprocal, and multiply. So what we end up with is x plus y over y multiplied by x over x minus y. And that's nothing more than x times quantity x plus y divided by y times the quantity x minus y. they really aren't as bad as, I mean, they look bad initially. You look at that and think, holy crap. Let me have you try one on here. Here's part A. You guys do part B, or at least as much as you can. Try to get as far as you can on part B. Ooh. Hold on, I'm finding a good one. Yikes. Okay, X. Let's see what the answer actually is. It's probably 4. It's not 2. This side, we need an x over x. Over here, we need a y over y. So it looks like we're going to have x squared minus y squared over xy. Over here, we're going to need a y squared. Here we need an x squared. So we're going to get y squared minus x squared over, y squared x squared. Now what? Where's that?
On the bottom. No, it's y squared minus x squared over x squared minus y squared. Yeah.
Did you get it?
Yeah.
Okay. That's all right. That's all right. Let's so this top fraction, nothing happens with the top fraction. X squared minus y squared over xy. But we do have to flip the we got to flip the bottom fraction here and change this to multiply. So multiply by y squared x squared over y squared minus x squared. Holy moly. Now these look so dang close, but they're not exactly the same, so they can't cross cancel. What about any of these guys here, though? What do you think? No? Yes? Maybe? Possibly? The answer is yes. Y squared or...
For the negotiations, can you send Nicholas Mansfield to the front office, please?
Yeah. Nick would speak up because I don't know. I'm glad you're here, Nick. So y squared is really y times y, and x squared is x times x. So one of those y's cancels with one of those y's, and one of those x's cancels one of those x's. So we have xy quantity x squared minus y squared over y squared minus x squared. And, wait, aren't we done with this one? Or are we? Or aren't we? To be continued, huh? We're not actually done. Dang it. What could possibly be wrong with this? Factor, yep, keep going, factor.
The difference of squares.
The difference of squares, right? X squared minus y squared. That can factor into x plus y times x minus y. See, isn't math cool? And then down on the bottom, y squared minus x squared, that can factor into y minus x times y plus x. And then we have a common factor, do we not? The x plus y and the y plus x. Addition is commutative, meaning order doesn't matter with addition. So now we have xy, quantity x minus y, divided by y minus x. Oh, man. Let me show you something else. There is another way to do these problems, and sometimes actually it's.
Can I have Chad Articulo to the attendance office for a minute, please?
Who is that?
Chad Articulo.
Okay. All right. She said 1 minute. I'm counting. 1 minute. She said 1 minute. Does that count for the time you're walking or just when you're down there? What do you? Probably just when you're down there.
Yeah.
All right, so I'll give you 1 minute to walk. 1 minute down there. So 3 minutes. 3 minutes tops. So sometimes this method too is a little quicker. Let's see. Oh, no. I don't want to write it again. I'm going to copy it. Ooh, look at that. Okay. So, if every single fraction on here had the exact same denominator,
If we were to get them all to have the same denominator, what would the common denominator be? Of all the fractions. If all the fractions, x squared, y squared, wouldn't it? You guys agree? The common denominator would have to be x squared, y squared?
so what you could do is multiply the top and bottom by the common denominator. Because really, this is just 1, isn't it? So I'm not changing the value of this expression. So let me write this a little different. I'm going to put the x squared, y squared here, and put another x squared, y squared there. What's going to happen when we do that? What's going to happen there? Are we completely stumped, or have you just lost interest? What would we do with this? We would distribute it. And here, just kind of looking ahead, can you see what would happen potentially?
Can you see the merit maybe of this second way of doing it? What's going to happen here? It can reduce the amount of steps, but are we going to get rid of fractions? Here we're going to have this y squared is going to cancel with that y, so that fraction's gone. Hey. Thank you. Yeah, right.
This is like the pass of all passes. I can get into any athletic event in the entire state for free. Take that, suckers. Yep. High school, yeah. High school.
I was gonna say, like, that would be amazing.
I know. I take that to the jazz game. Can I use this at the jazz game? That would be cool. No. Come on, let's finish. Well, actually, is this the last objective, or do we have something else? We have something else, don't we? Darn it. Let's do the last objective, and then if we have time, we'll get back to this one. But I don't want to miss that last objective. Yeah. So this one was called rationalizing. Rationalizing. Oh. Honestly, this whole thing of rationalizing denominators is unnecessary nowadays. We still do it for some reason. I don't know. We really don't need to. The reason it came about, here's what rationalizing means. You learned about this in 7th grade probably, or 8th grade at the latest. But is this okay, 2 divided by square root of 3?
No.
It actually is now. But what is it that you learned back in 7th or 8th grade? No roots on the bottom of a fraction, right? So what would you have to do here? You have to multiply the top and bottom by the square root of 3. Why does it have to be this way? What is this expression right here? It's just 1. Am I changing the value of the original expression if I multiply it by 1? No. Whereas if you try to do this, then aren't you changing the numerical value of the expression if you try to square it? You completely change the number. So you actually can't just square it. You rationalize it, and you end up with 2 square roots of 3 over 3. That's called rationalizing. Why do we rationalize? Well, this predates calculators. Before there were calculators, have any of you ever seen a slide ruler? Or heard of one at least?
Yeah.
They used to have to use these, I don't know, it's been a long time, 30, 40 years ago. You couldn't divide by square roots on a slide ruler. You just couldn't do it. You could do this on a slide ruler, but not this. But now with the recent invention of a calculator, which isn't that recent, right? I don't know why we haven't caught up to this. If I typed in 2 divided by the square root of 3 in a calculator, would my calculator explode? No. This is kind of an antiquated notion. But 2 divided by the square root of 3, I guess I didn't do 3. Nope. 2 divided by the square root of 3 is 1.1547. If you do 2 root 3 divided by 3, they are numerically equivalent, and your calculator can handle both of them. But we're still living in the past, so we rationalize algebraic expressions such as 1 divided by 1 plus square root of 2. Now, truly the reason that we do need to go over this is in calculus, when you start learning about limits, sometimes an expression in this form doesn't work. You have to rationalize it to change it slightly, so you end up with something that does work. So this does have merit, this idea of rationalizing. And also when we get into trigonometry in March and April, we're going to have to do a little bit of rationalizing. So here's the thing. Here's what happens. Does anybody remember back in Algebra 2 when you had this expression like 1 divided by 1 minus I? Do you remember we had to multiply it by 1 plus I over 1 plus I? Does that sound familiar? That's called a conjugate. Does that ring a bell? The conjugate? The complex conjugate? Well, we do the same thing here. It's not a complex conjugate. It's just an irrational conjugate. We have to multiply by 1 minus the square root of 2. So in the numerator, we're going to end up with 1 minus root 2. You guys are clever, right? You guys are smart, aren't you? You can recognize patterns. What is it when you have the same identical binomials, but one's plus and one's minus? Do you recognize that pattern? Isn't that just the difference of squares, right?
Yeah.
So rather than having to do the whole FOIL method, like first, outside, inside, last, if you could just recognize that This is nothing more than the difference of squares pattern. I'm just saying it shortens the process. If you don't know what I'm talking about, then just use the whole FOIL method. 1 times 1 is 1. 1 times negative root 2 is minus root 2. 1 times root 2 is plus root 2. And then we have minus the square root of 4. That was the FOIL method, yeah. Wait, where did that square root of 4 come from? Square root of 2 times square root of 2 is the square root of 4. Okay? Now this minus 2 and the minus root 2 and the plus root 2, those cancel out. And the square root of 4 is just 2. So we end up with 1 minus the square root of 2 over negative 1. I probably would give you full credit if you left it like that. Most textbooks would, because it is kind of weird to have a negative 1 at the bottom of a fraction. So they would probably change it into this.
Well, this is square root of 4.
The square root of 4 just changed into 2. Where did it come from? Oh, I just changed that into a 2, and then 1 minus 2 became a negative 1. Does that make sense? But most textbooks would take it a step further and call that negative 1 plus the square root of 2. It does look a little bit nicer, I guess. I don't know. Okay? But just kind of to reference what I was trying to explain just a second ago. This pattern was difference of squares patterns, yes? So really all this is your a value squared minus the b value squared. 1 squared minus the square root of 2 squared is just 1 minus 2, which is negative 1, right? Save you a little bit of time if you recognize that pattern. Anywho, man, I think we better be done, y'all. That was a lot of stuff, huh? Holy smokes. Oh, yeah, let me stop recording. This is like a 2-hour long video. It's going to be 500 megabytes.